All right, hi everybody. Well, I want to have our next lecture. We're still talking about the Colpitts Oscillator, and we're going to keep digging a little bit deeper into that. What I want to try to cover today, I want to do a few things as we go down our list of items that we want to cover in this. I'm going to just we've talked about the background already. We're going to dig into a little bit more of the characteristics, talk about the butterfly effect, or at least in this case, the sensitivity to small changes. Want to demonstrate that, as well as the Poincare surface. And do a little, today I want to do some Matlab demonstration, which I will then share with you that you can try and implement as well, and then we'll make sure that you can do all of these things that build your skill set. All right. So let me start again by just describing what this Colpitts oscillator set of equations are as it relates to this circuit. As I mentioned before in our last lecture, you have a current that flows through this inductor L, so that is I sub L. You have this voltage that is part of the collector of the transistor. This is the emitter of the transistor and the base. So the collector voltage is V sub C, and the emitter voltage is V sub E. Okay? So with all that in place, you set up these equations that tell you what's going on. Now, as you see, these equations are in terms of a time-varying differential. So this is a set of three-dimensional ordinary nonlinear. Let me get rid of that. That looks like an H. Nonlinear differential equations. And the difference in terms of time, right? dt. Now, you may know from just general physics that something with respect to time, change in time, is a velocity with respect to what's changing. So it's the velocity of the current, the velocity of the voltage, the velocity of the other voltage. But in electrical engineering terms, L di dt is a voltage. So these, as you can see, are all voltage expressions. And let me do something, because this thing keeps keeps jumping around, and I want to get out of that. All right, let's see if this works better for us. Well, now red will be fine. All right, so I want to change from red when I do the equations. So see, is there a way to change it? Change the color. I don't like the red color. Okay, we'll go back and forth, I guess. Okay, so these are voltages. So L di dt is a voltage. So that's a voltage, and R times L is a voltage. But C dV dt is a current, and this is a current expression. That's why you see IL here. V over R, that's a current. Same thing here. dVc dt is a current. This dV dt is the same as the one up here, and so it's also a current, as well as this and I sub c, which is described by that expression right here. So that's what this is. So this is all a set of equations balanced together to tell you what's going on. So in order to analyze it, you have to solve these equations so that you can get I sub L as with respect to T, VE with respect to T, and VC with respect to T. Okay? That's what you're trying to do. And this circuit over here helps you figure out what actually is going on. All right, so as we also said, when you start to solve this, you can get something that looks like this dependent upon the values of the parameters. And those parameters are things like R, RL, VEE, RE, C, CE, so on and so forth. Those are the parameters of the circuit, which means the value of the inductor, the value of the resistor here, the other resistor here, the capacitor here, the capacitor there, the voltage that you're applying right here, the voltage that you're applying right there. All of those things are parameters that then determine what this thing, how this thing behaves. And of course, the transistor element is described by this exponential equation, which has a constant to multiply, another constant that is multiplying the voltage V sub E. So it's nonlinear in that regard. And that is the only nonlinearity that exists in this system. Now, we talked about Lyapunov exponent, and we're going to actually demonstrate that using Matlab here in a second. So here's a set of parameters that will get you this. So you can see all of the capacitances, the resistance. This alpha is actually, well, this beta, I should say, is actually what we've called gamma that you'll see in some places. Just use that just for the computer's sake. VCC, the inductor, the resistance, so on and so forth. All of these, and then this time step and the initial conditions. So this is a set of parameters that would get you this type of behavior. All right, so what I want to do first is I want to clean up what I tried to do at the last lecture, just kind of clean up these equation, trying to figure out the focal points, or foci, that it's called in some places. I'm going to get back out of this because it keeps jumping around. Or I don't like this red, and I haven't figured out how to change it from being red. It's black when it's under it like this, so I'm just going to write on this, but of course it keeps asking me to do things that that I don't want to do. Let's just see right quick if this will work. Nope. All right, so it's just going to jump around a little bit, but don't worry about it. All right, so this is what we're going to do. Let's go back and start with this equation right here. Now, as I said, these are velocities, right? And what we can kind of assume, because this is a thing, let's go back to this, that winds around in state space like this. And I'm just going to assume that's the direction. But let's say it winds around in that. As you get more and more to the center, the velocity goes to 0. So we're going to use that as a way to try to figure out where the center actually is. So essentially we're going to set these equations equal to 0. So if I said VCC minus V sub C minus, yeah, this was I was afraid of, it's jumping around, That's a minus sign. Minus R plus RL I sub L. Okay. Equals 0. All right, what we're trying to do, we want to come up with a place of IL, VE, and VC that's in the center. This is what we want to find out. Where's that center point? So we'll call it, you know, little sub P for each one. Let's just say that's the center point. Okay? All right. So right off the bat, we've got V. We could let's just try to solve for VC here. This will say VC. This one right here. VC is equal to. I'm just going to move that over and leave the rest. VCC minus R plus RL times I sub L. Okay? All right, so we'll leave that for now. And I'll circle or put a box around that for you to just keep that. And we can call that VC sub P. And that could be sub P because that's what we're looking for. All right, now, so let's go to the second expression. And in this case, we'll have, and I'm going to move that over and leave IL by itself. So we have I sub L equals C E, well, no. Hold on. This is, all of these are going to 0. We set that at 0. So I sub L is just equal to VE minus VEE over R sub E. Or let's just make it say V sub E over RE minus VEE over RE. Okay. Okay, so we'll leave that as it is. And then finally, in this third one, remember that's 0, but also this dVE dt is also 0 because we set that equal to 0, and we're going to assume that the capacitor up here is not 0, so that must mean that dVE dt is 0. So that's 0 too. So from 3 we have IL minus I sub C equals 0. Okay? Which says that IL equals I sub C, which is equal to gamma times E to the minus alpha VE minus 1, which is basically that, right? So IL is equal to that. So we've got some things we can work with. Got that. We also have this. Okay, so let's go to the next page here. All right. So we know that IL is equal to VE over RE minus VE EE over RE. And we also know that IL is equal to gamma times e to the minus alpha VE minus 1. Okay? So, what we have here is an exponential in VE, and we also have a VE over there. All right? So that helped us to, you know, a little bit anyway. Okay, so we're going to just move some stuff around. We're going to take this gamma e to the minus alpha v sub e. All right, and we're going to say that's equal to this. There's that VE over RE minus VEE over RE. And then that's a minus gamma that comes over, so now it's plus gamma. All right? So we're going to take all of this, and let's let that equal to y. So in other words, I'm saying y equals VE over RE minus VEE over RE plus gamma, okay? Which we can now solve for VE in terms of that. And in that case, if I want to do that, I'll say VE. We move all that over there with the y. So that'll be VE is going to be equal to y plus VEE over RE. Move that. Minus gamma. And then after we moved all that, then we're going to multiply by RE. And now we've isolated V sub E. Okay, and that then, if we just want to clean it up a little bit, that's y times RE plus VEE, because the R's canceled there, minus gamma times RE. Okay, so those are those things. All right, so now if you see, this is VE, right? And this is VE. So we can say that gamma E to the minus alpha VE is equal to gamma E to the minus alpha times y times RE plus VEE minus gamma RE. Okay? Now, if you know with exponentials, this, you can also just break that into multiplications of it. So this is now gamma E times e to the minus alpha YRE, all right, times, well, gamma multiplies everything, so let me just, now this is multiplied time, let's just do that, e to the minus alpha VEE times e to the plus alpha times gamma times RE. Okay, so those are now these values are constants. This one here and this one here are constants because those, you know, are fixed. Y is the only thing that kind of changes, right? So, let's go to the next page. So remember, those are constants. I'm going to call that A. So I'll just say A. Let A be equal to e to the minus alpha VEE times e to the alpha times gamma times RE. That's what A now is, which is just one big constant. And we know that so this is now A times e to the minus alpha y RE, so E, is equal to y. Okay, we know that. Okay. Now further, we could just let, so now I'm going to move the E over here and say that y times e to the plus alpha y RE is equal to A. And that's a constant. So I want this kind of in the form of just, let's say, z e to the z, right? And this is what we mentioned me talking about before, is a Lambert function. Now, I'm not trying to imply that z is a complex, but it's that's just a form, right? So let's allow z is going to be all of this right here. So let's say z is equal to alpha y RE. Then that means that y is equal to z over alpha times RE. So this then will be z over alpha RE e to the z is equal to A. And we could just make another constant if we want, but z is equal, z e to the z is equal to A over alpha times, not over, multiplied by, is equal to alpha RE times A. Okay, so the process would then be, we could go to our lambda table, find out, because A can be calculated, so now if we go back, remember A is all of these things over here, so A is, e to the minus alpha VEE times e to the alpha gamma RE. So all of that is a constant. These values, all constant. So that's just a number that you can calculate. And so is, alpha times RE, which is down here. So you can get that lambda function if you kind of remember what it looked like. It had a funny looking shape, something like that. And this was, for the value z, and then this is z e to the z. So you can find out what this value is, right? Which, if you find out what alpha r e times a is, be something, say, in here, then you find the corresponding z value, and now you know what z is. And when you know what z is, then you know what y is, because remember, y is z over alpha re, and if you know what y is, then you can know what ve is, because ve is equal to y plus VEE over RE minus gamma times RE. So that's what VE is. And now we can give it that VE of P. So we figure out all that stuff. Now you have VE of P. And if you have VE, then guess what? You can now go, and get what IL of P is going to be gamma times e to the minus alpha VE of P minus 1, and VC, as you go further up, is equal to VCC plus R plus RL times IL of P. And then I'll just write the other one again, where VE of P is equal to Y plus VEE over RE minus gamma times RE. Okay, where y is equal to z over alpha RE, and z is equal to where did I don't want to go in circles. You got y. Yeah, y. Where did I let z equal to? Oh, z is equal to where did I? Yeah. Oh, sorry. Nope. Oh, it's y. It's y that I'm going in circles. Hold on. Y, if I go back up here, y is equal to VE over VEP. Let's call it P now. Over RE minus VEE. So be EE over RE plus gamma. Okay. So now everything is in terms of what we know or what we can find out, and you should be able to get all this. Now it's complicated because, and I just want to go through that because you know, you asked for doing this circuit, and we did. But the thing that ends up making it complicated is the exponential and the transistor. So as simple as a circuit as that might look, it's still very complicated in the transistor that is used to describe it. You know, this right here. But when visually and when you calculate it, you can get to all this stuff. All right. So now what we're going to do is I'm going to look at Matlab a little bit. So let me bring this down and bring this up. And let me just show you. Hopefully you can see this. I don't know if I can actually make the wording bigger so you can see it from here, but I'm going to also make sure that this code is there for you to look at. But this will run the it will integrate the equations according to a set of parameters. And so here's one set that we're using. And we have different sets. Here's another set, slightly different. But the way I'm setting it up is that you could go in and change these parameters a little bit and just keep running it. And that way you'll get a little bit of different behavior. But this is the code that runs everything. This sets some initial parameters. The Colpitts parameters it pulls up. So if you see this says CP parameters 1, so that set right here is what we're going to use. This is what's going to be a Poincare surface. I'll describe that in a second. It's going to integrate and it's going to produce the output, and you're going to see, because this will actually do all the plots, you're going to see that. So we're going to go ahead and run this, and in order to run it, I'll just type in Colpitts analysis. That's the name of the code, and it runs it. Now it's running it for 50,000 points and integration points, and it's finished already. So we could do more, and I might do more, but I don't want to talk about these curves yet. Let's get to this stuff. Now, first of all, I'm going to make this bigger. All right, so here is the flow, the integration of this flow. It's pretty nice and well defined, and it's whirling around in a in a direction. And what we did was, first of all, let's pull up the plots that show each projection. All right. So here's, if you're looking at it from the standpoint of Isabel, which Isabel is kind of X, so you're looking at it in this direction, and only V sub E. So you're looking at it in one projection. This is another two-dimensional projection. Here's another two-dimensional projection here, here, and here. As you can see, there's kind of a nice defined hole right here, which allows us to establish. Here's another one over here. And here's one. This one's a little less. You might want to not get dead in that center. But so a Poincare surface, if you think about this three-dimensional space, you're going to slide a flat two-dimensional sheet right down through it and cut through it. And when you do that, it's going to pierce that surface at these points. Okay, so let's go back to the three-dimensional picture. So this surface, if you can see these dotted lines, it's set up here. Now I'm gonna go back to the Matlab code and I'll show you the actual numbers of what defines the surface. Okay, so it's set up. So this PSSD. So this is the X, Y, and Z boundaries of the surface. So if you see here in X, it goes from 0.005 to, well, 0.0075 to 0.005. Now if I go back to this, and I'm going to make this smaller so I can look at the numbers and talk about it at the same time. If I can, there we go. All right. Go bring that over here. All right. So if you can see that, so in IL, so remember X, or the first item is I sub L, which we call X. That's over here from 0.0075 to 0.05. So it runs along here, along that direction. The next is what we would call Y, which is this V sub E, but that's fixed in one position, minus 1.4, which is right here. If you project that over, you'll see that that's right at 1.4, negative 1.4. And then what is it doing in Z? And that is what we call V sub C, as you can see there. Right here, that's V sub C. What is it doing? It goes from 0 to 9.6 up high. All right, so that's the extent of this surface that you're putting through it. And now if I should be able to kind of rotate this around, yeah. So if you see that, you take a look, you see that that surface is set up in such a way that it's cutting through that flow, and is picking up the points that pass through it. Now this isn't necessarily the best place to put, and we're going to try some other surfaces. I mean, frankly speaking, I think maybe putting a surface that cuts across this might be the best, but we're gonna do that a little later, or I may ask you to try to do it. But this code right here called get PSS will pull all the points that pass through it. So now what we're looking at, now let's take a look at the actual surface, and this is what you get. So this is what passes through that plane. You can almost think of this graph, the boundaries of this graph as the plane, or part of the plane. You can see here from 0.01 over to 0.0024. This is from 3 to 9. This is what comes through. And if I'm not mistaken, it's about 400, almost 500 points that pass through here. So this is what cuts through. So this is a sheet. So so you can think of this chaotic flow almost like this sheet that's bent, and when you put your surface through it, these points are passing through. So this is this. Now, one more thing, if you order this in such a way that says, okay, here's a point that passed through. Now, where's the next point going to pass through in either IL or in VC? So if I have a point that comes here, where's the next one going to come through? You can figure that out because you have this sequence of points. And so if you do that and order it in what's called a return map, here is the return map with respect to the current. So now if I look at this, and I'm going to see if I can draw on here. No, I can't. But if I was to look at this, if I have a point that comes through here, and And this is set up like a straight line. Remember how we projected with the map? This is the same kind of map as the logistic map that we talked about, but you see two humps. So anyway, you can figure out where the next point is going to come out, and you can do the same thing for the collector voltage V sub C. Same thing. This looks a little bit more like our other map. It just got this little tail at the end over here. I want my mouse to show. Little tail over here. But it has that single hump map. And you can believe that there will be a bifurcation diagram that could generate, and I'll try to do that for the next time. But one thing I'm going to do before we end up here, I'm going to change the parameter a little bit. So I'm going to use the same value here. So I know that by making this resistance value a little bit bigger, it's going to shrink the attractor, and it may not even be quite. So I'm going to make this 102. All right, so I'm going to save that, and now I'm going to run it again. And now, so let's take a look at so look at this. Not only is the attractor smaller, but it has a periodic structure to it, which also has, as you can see in the map, there's only little bitty points that show up. Same thing, these projections. This is a periodic flow because it ends up coming back on itself. And once you do that, so let's try again, and let's this time. So I'm gonna make it a little smaller. So it was 92 before. I went to 102. So let's make it 96. Okay. Save that. We're gonna run it. Oh, I didn't want to run that. I want to run this. All right, it's spreading out a little bit more. Here's the attractor, but it's still a periodic orbit because eventually it goes back on itself. It's not repeating like the other one did. Okay? So you can, when you get this code, you can play with that, and you can find some, you can play with all the parameters if you like. You know, just make sure you remember what the good ones are, and keep a copy or set of it. But let's go back and try to maybe make this another. So it's 96. We know that the smaller it gets, the more chaotic. Let's go the other way. Let's go to like 75. And let's just see what happens. It may go crazy on me, who knows. Well, see, now you see even the map looks stranger. The attractor has grown because we're plotting this over some specific bounds, and I could expand that, but I didn't do it yet. And the surface is not even necessarily in the right place. So as you can see, as you play around with this, somewhere around 80 is a good number. So let me go back and do that, and then we'll end up. So let's say 80. Let's do that. And it's similar to what we had before. So a good, nice, smooth parameter for that might be somewhere in the 90 frame. So let's just say that. Well, Well, as you can see, you could get caught up into doing a lot of this. So, but that's a nice size attractor. So if you found a value that gives you a little bit more flow, this is a very high periodic oscillation still, okay? So you can play around with that yourself, and you can see what happens as you just tweak different parameters and tune it to give you something that you want to play around with. And analyze more. So we'll do that. Next time, I'm going to also take a look at the Poincare surface some more, and a bifurcation diagram, try to see. So you think about what it is that you think we could play around with to generate a bifurcation diagram. We got a few parameters to mess with. As you can see, that R might be a good candidate, right? What happens as you change R from smaller to larger, what happens, and how could we capture what's actually going on? Well, we'll explore that and others in our next lecture. So hope you enjoy yourself, and hope you enjoy this lecture, and just let's keep going after it, okay? All right, take care.